Good morning. Good. So let's talk about resiliency but before we get there, are your systems resilient? Do you think that your systems can tolerate failure? If you look at what you have been building, any thoughts, do they? And if so, how do you test that? How do you verify that? Yeah, my system will tolerate failure. My system will tolerate latency from a downstream system. My system will tolerate another system I depend on breaking and not working. How have you been doing that? Well, if you don't know or you haven't done it, no worries, you're in the right place. So let's have a look at that. Quickly about myself, so I'm a senior technology architect out of the Helsinki office. I don't look Finnish, that's because I'm not Finnish, it's a long story. I'm from Spain, but I've been here a number of years. I've been at Accenture now for over 10 years and always doing technology architecture. Right now I belong to our emerging tech group, and I'm also globally responsible for pushing the containers and microservice agenda for our clients globally. So this is stuff that the whole resilience, cloud containers, microservice I do on a day-to-day basis. So hopefully I can bring in some of my experience here and help you guys, at least get some ideas on how we could be doing this a little better. But resilience, what's resilience? English is not my mother tongue, and I really didn't want to make up a definition, so I went to Wikipedia, copy-paste, and a second later I came up with this one. So resilience is the ability to sustain our applications' service levels under challenges of normal operation. Right? Something breaks, something goes slower than it should. The network suddenly partitions and we can't read something. So having systems that can actually put up with this is what all the resilience is about. And why? I mean, resilience is something we have been thinking about for a long time. Like I was building SAP systems a few years ago for Accenture, and we're always thinking about fault tolerance and replicated database and master-slave things with Oracle and Oracle RAC and all those expensive things now. Nowadays, what we're thinking that everyone should be thinking about it. We're moving into this digital world where we have IoT, we have cloud, we have all sort of SaaS services we have microservices, we have front-facing application, we have APIs. And these things are increasingly more and more, as we build more of these digital platform, digital services, they're seeing a lot more load than they ever did. They're becoming a lot more important for I hope, your businesses, right? So it's more important than ever that it's not just about making our backends, SAPs, ERPs resilient. It's about making everything around it. As we build ecosystems of APIs, as we build front-facing things, as we allow third parties and partners to talk to our APIs, this becomes more important than ever. So, this is the kind of architecture we often build, very standard stuff. We have our data stores, we have our integration services, we have our APIs, or like a composition of calls to even more underlying systems, and this is pretty standard, right? Or I would hope that this is pretty standard by today's definition of digital architectures, and it's good, right? We have we get components are decoupled, and it's great. If you just attended the Zalando talk, that's what they were saying. You can have smaller components, each one with very independent and very specific purposes, driven by separate teams. It's actually really cool, right? Scalability. So again, the Zalando guys were saying, well, we have the search, and the search is very busy, so we can scale the search service, we can scale the search data stores to make it go faster. It's actually really good for our architectures. It's agile, right? So we can work on specific components at any given time without having to worry about everything else. We all communicate over APIs, and the world is great. And also from a DevOps perspective, we hopefully no longer have a big monolith. We have, again, smaller components. We can develop one, release it whenever we want without really having to worry about everything else that may be underneath downstream in our layer architectures. And of course, we can also choose the best tool for the job, right? So we can choose different frameworks for different services, different components, different data stores, different technologies, different clouds if we want to, right? So it's actually, if the world was perfect, this would be the end of it. It's great. However, we know architecture, it's all about making trade-off, right? So now I have smaller components that I can scale independently, I can deploy anytime, I can put them anywhere I want, across clouds, I can do a lot of things. But what are the problems? The first and most important is now you have a distributed system. The moment you start making calls to complete your processes, that is a distributed system, right? And everything is a remote process call, right? So you need some data. Well, that service has it. Well, let's call it over HTTP. But that's not going over the network. And we know, or I hope you know these things by now, the fallacies of distributed computing, right? The network is reliable. Well, it is until it isn't. And then when it isn't, what do you do? Well, I didn't think of that actually. Latency 0, but we know it's not. That's clear. The bandwidth is infinite, yes, but it's not. Right? You can go to Amazon and you can start making really fast calls. Well, this actually puts up with it, but then, oh, wait a second. I just maxed out the bandwidth of my EC2 instance, and my service isn't ready to deal with that. So, we should have tested that sort of stuff. The network is secure. No, nowadays it's not, right? Topology doesn't change. That's not true. There's one administrator. Well, we just heard about the Zalando guys, very exciting stuff. When I asked them, how do you maintain these things? Well, different teams maintain their own services. Well, then how many admins do you have? I'm sure they don't even know. Lots of them, right? So it's not really, there's not a single administrator anymore. Transport cost is 0, it's not, and the network is homogeneous, it's not. And these have been there for a long time. These have stood the test of time, but they become more important than ever the moment we all have a distributed system, and we do, because that's what we're heading to. And what if it breaks? Well, what happens? We have our architecture, and we have things, where's the mouse? So, connectivity can break between services. Latency can suddenly increase. Amazon is pretty reliable, but every now and then you'll see peaks in latency for calls between availability zones, right? That can happen, and it's perfectly normal. But we need to be able to deal with it. The problem is, if we're not prepared for that sort of stuff, failure in one of our downstream services, whichever it is, it starts cascading upwards. It affects the service on top of it, and it affects some other composite service that was using that data, which eventually affects our web application, which eventually slows down our clients, our mobile applications. It slows down everything. So we have this problem with cascading failures. So how are we approaching this nowadays? What we're saying is failure is a feature, embrace it, really. We have to just deal with it as gracefully and as nicely as we can. We just embrace it. And we being architects, and I know Thomas in the morning was saying, it's not really about patterns, but I don't care. I like my patterns. And I think patterns are clear and established solutions for solving problems. These are a bunch of patterns. This is not an exhaustive list. There's many more of these. But typically, the way we approach these sort of problems, typically timeouts, fail fast. I'll cover some of these. Isolation, bulkhead, circuit breakers. And then on the other side, we have somewhat more complicated ones. The actor model, it's a pretty exciting stuff, but that could be the scope for 10 talks in a row. It's a pretty exciting stuff, but very complex as well. Load shedding, non-blocking I/O, redundancy, and back pressure. Today, since our time is limited, we'll concentrate on these ones because they're pretty effective. Doing this stuff can actually solve a lot of our resiliency problems. And in addition to that, there's tools available out there, there's frameworks that can actually very, very easily help us address these things in a very simple manner. And that's, again, linking this back to Thomas's talk in the morning. It's about the democratization of IT, right? Specifically, we'll talk about the work Netflix has been doing in this area. And then Netflix said, well, I'm going to put this in open source. And thanks to that effort, thanks to some of the things happening in the Spring framework, we can actually do this quite easily nowadays in our applications. So let's have a look at some of these patterns. So first of all, timeout. So obviously, typically we will know how long it should take to make a call to one of our downstream services, right? So many times we don't bother setting timeouts. Many times we will take, we're making a call, we'll take the Apache HTTP client or the Spring REST template, we'll make a call. And then the question is, well, what's the default for that call if the service starts responding slowly? I don't know. I don't even know nowadays. So what we're saying is, if you're going to be making calls, it's really easy, it's really simple, and I'll show you later a couple lines of code. Make sure you're setting as aggressively as possible a timeout for your calls. It's really simple. It's almost common sense, but you'd be surprised how many times we don't do this. Right? If you know you're going to make a call and you know how long it should take on average, set a timeout around that limit to prevent scenarios where your service starts failing because it's overloaded, because the network is really slow, because of whatever reason that the service is there but not responding. Make sure you set a timeout. And same thing for any other of your downstream dependencies, even to your data stores. That's possible. Maybe you're running an Oracle database, you can set a timeout. Maybe you're running one of these modern NoSQL databases that actually operate over HTTP and over REST. Even easier, set a request timeout on your HTTP client and be done with it. It sounds trivial because it is, but again, I wanted to bring this up because it's something that we're not really commonly doing, and it's really very important. The next one is failing fast. So obviously, you know your service is failing, or one of your downstream dependencies is failing, right? So why should you wait for the whole time, even for the whole timeout, to actually tick and pass and then return a failure? You know it's failed. You know possibly for the next 5 minutes or for the next 100 requests it will keep failing. So don't even bother trying. Just make it fail right away, and potentially return maybe, I don't know, your last cached valid response, or return some empty list of data that says, okay, well, it returned but it failed, or didn't just fail but failed right away, right? So kind of the again, aggressively saying this will fail, I'm not going to try, so there's the error, I'll try again later, maybe in a few minutes. So that's the fail fast idea. If you know it's going to fail, if you know it's failed before, it's likely it's going to fail for the near future, then just keep failing again and do it as soon as you can. The next one is the isolation that comes. It's very much like what I said a couple slides ago. So a failure in one of your services should not affect the surrounding services. If your data service, like in this picture down here, fails, make sure it doesn't really affect the business APIs that are on top and using it, and so on. So this is again kind of trying to keep your services isolated from each other as best as you can through some of the patterns we are now discussing. And the next one is the idea of bulkheads, and that's easier to explain than to draw. Typically, you will implement bulkheads in Java using thread pools, right? In a web server, typically, if you run your application on Tomcat, you'll have a common thread pool of requests, HTTP request processing, and then you'll make a request to whichever other service downstream in the same thread pool. But what this is saying is, if you separate your calls into different thread pools, then starvation of one of your thread pools for calling some services will not necessarily affect another thread pool for calling something else in the same service and in another service. Right? So you kind of bulkhead, kind of separating, isolating, splitting different purposes, typically in the Java world through thread pools. And the last one, and I think it's the most important one, or at least the most exciting one, is the idea of the circuit breaker. So the idea of the circuit breaker is that it's a very simple state machine with 3 states: closed, open, and half open. So when everything is okay, the breaker is closed. So something is happening, it's happening okay, no errors, no problems, let it keep happening. However, at some point it will reach, a failure will happen. There's a threshold for the number of failures that can happen, it's configurable, and we'll see that later. And therefore the circuit will be open. At this point, nothing goes through because it's been failing. And if we think back, 60 seconds ago when I said it's failed 5 times, it's likely that in the next minute it will keep failing. So the circuit breaker will not even let you try. It will tell you this has failed, it will keep failing, this is your error, deal with it. But it will give it back to you. It will give you an error, in a matter of milliseconds. You won't have to wait for any timeout. You won't have to wait for the service to respond to get an error. It will happen right away, right? But the circuit breaker, and we'll see one of the libraries that does this later, it has a timeout. And every now and then it keeps checking. It will let 1 or 2 requests through, keep checking what happens, and then it will tell you, well, actually the last one worked. I'm going to kind of half open and start allowing some calls through to your other services. And then it remains in this half open status, which keeps being monitored. And if it fails again, then it's going to get closed once again. But if it works, it will go back to the closed state, right? So it will allow calls once again, right? So it really works with these 3 statuses. Closed, it works. Open, it doesn't work, I'm not going to let anything through, but then it keeps checking, well, something went through, let me keep an eye on it. It remains half open. If it keeps working fine, it will open it again, and then calls will start again flowing through. And we'll see this in an example. It's actually a lot easier to see over there. So hopefully by now we deal with failures like a boss, but we need a tool. Luckily for us, there are tools. And that's what I was saying a couple slides ago when I talked about the work that Netflix and Spring has been doing. Netflix, we know by now, I'm a heavy Netflix customer. I guess many of you are too. If you look behind the scenes of what they have hundreds of microservices across their application state. And obviously, their architecture is incredibly distributed. They have a massive amount of calls going through services back and forth. So if there's someone who will be hit by failure, it's them, right? Because they have so many nodes, so many services, so many calls across nodes that they will be dealing with failure. They deal with failure every single day. So one of the things that they actually came up with was an implementation of the circuit breaker pattern. They call it Hystrix. It's a library. And there's a very nice and clean implementation for Spring Boot, and that's what I'll be demoing later. And what can Hystrix do for you, and why I think it's so awesome? It will help you with the fail fast. It will help you, it's a circuit breaker. It will help you with the graceful degradation, and it will help you with bulkheads and the silent failure. And that's why today we're concentrating on this, because we can actually really very easily see how they work in Hystrix and see them in practice. So why don't we do just that? Let's have a look at Hystrix. We have a small demo set up here. So I have my trusty to-do application. Surprisingly, it lets you track to-dos, which is easy enough, and it gets the point across. And then it has a client, a web client, so you can add to-dos, you can see what's in the database. And then for the purpose of today's demonstration, we have this service view over here that actually makes calls to the to-do backend API. And that thing looks like this. Let me show you. It actually works on a Docker container. So I'm just going to start the to-do service. And I had already running it, so it's actually quite fast. Great. And then it's quite simple. It's just you go to the front page, and then you say work hard. It works. Give a good demo. Have a beer later. Important things for today. And then this is in the database, so it works very well. And then it actually has, which one is? This has, oops, AD. So there's an API. It actually gives me the to-dos in JSON format. So what I did is we have a very simple client that actually makes calls to that application. And it's simple enough. It's written in Spring Boot. In terms of framework, Spring Boot actually is pretty good nowadays. We're using it a lot for building microservices across many clients in Finland as well as abroad. It's a great framework, and that's why I chose it for today. And essentially, we can actually run my service. And again, it's simple enough that it's going to work right away. So it's running. It's great. Let me find my browser, and then I can go to port 9090 and then call for my to-dos. Well, it's great. It works. I'm a really good developer. I can actually call my to-dos. But I'm not living in a fantasy world, and I just told you, I heard Oscar saying that failure will happen, so what can I do to actually prevent this failure from happening? So we need to add, he said, we need to use a circuit breaker. So how hard it is to use a circuit breaker in Spring? Well, it actually happens so that it's very easy. And I'm going to cheat. I've already written the code, and I'm just going to change to a different branch in Git that has the code in place. But just to give an idea, this is Spring Boot. And I know it does a lot of magic. It's all Java annotations. And I know some people have an issue with annotations. But for things like this, I don't. There's a whole lot of AOP and dynamic programming and proxies being built in here. But essentially, take your Spring Boot app, annotate with one class, one annotation in your main class. And then you go to your service. It's a standard Spring service, makes calls to the other side of the fence, and then annotate your thingy with Hystrix command. Really, that's all you have to do. And again, there's a whole lot of magic here. If you do not like annotations, you can control the Hystrix library with normal Java calls. It's perfectly possible. And then I have my service, and that's what I was talking about in the beginning, the timeouts. I know my service should never, ever take more than a second to respond. And if it does, then there's a problem. So what we're doing here is I'm using Spring REST template. It makes it really trivial to call RESTful endpoints. So I'm defining a timeout of like a second, because I know it shouldn't take any longer ever than that. So this is great. I've added the necessary code very quickly, but I hope you got the idea. I've added the necessary code for making calls. So let me run my service. Again, now with the updated logic for handling histories, for making my calls with histories. And this is now running. And I can go to, I lost it. I can go here and I can do calls, and that's pretty good. It works. It's great. That was easy, right? Adding histories. I'm a really good developer. I can use these tools. This is awesome. Okay, but now I'd like to know, wait a second. We stop our service. Now what happens? Something will go wrong. So how do I actually show that? Actually, no, we're going to see something else. We're going to see the Historics has a dashboard, which essentially, you know all the states I was talking about for the Historics, so the circuit breaker, open, half open, closed? History gives me the means to actually see that visually, and it's called the dashboard. And continuing with our Spring magic, I go to my application, I annotate again with enable Historics dashboard, and that's it. We can be even better developers because Spring does a lot of magic for us. And how does it work? So I start my service. Takes a few seconds again. Okay, it's there. And then there's actually, where's my, yeah, here. I can go to a specific endpoint, which is /historics. It opens the historics dashboard, and then I point it to historics stream. This is now pointing to itself, but I'll show you later how to do this on at a scale. And then monitor stream. And there's actually nothing happening, but eventually there will be something happening. So this is my historics dashboard. Essentially, I'm going to flip quickly to the slides, and I'll show you what it has in there. So basically, it's showing us this kind of circle in the middle. It'll be green for whenever there's a problem. It'll turn red and redder as there's failures. So you can see also what's happening, and you can get an idea of the volume because the circle keeps growing and shrinking. It will show us the relative change in traffic in the 2-minute request rate, so we can actually see how many calls are going through my circuit breaker. It will show us the number of hosts connected, the median, the mean. It will give us some data about the operations. It will tell us the name. It will tell us the error percentage. So I can actually visually see how many of my calls are failing through the circuit breaker. And then it will show us the request rate and some last-minute latency percentiles, which is pretty nice. So I can actually, I have a small Spring, JMeter test here that I can run. And essentially, this is now running 2 threads. But you can see my circuit breaker actually now in real time showing what's happening. Right? So I can see there's plenty of traffic, about 50 requests per second, which is matching with what JMeter is saying. Somewhere down here, it's about 58 per second, roughly what Historics is seeing. And this is pretty nice. It tells me it's closed, so it means everything is OK. Calls are going through. My system is perfectly resilient. Well, there's no errors, obviously. It's resilient. And it's working well. So that's the actual dashboard in Historics. But so much about failure, we haven't really even discussed or even seen. How can I actually test this? How can I simulate this sort of failure? How can I simulate latency? How can I simulate packet loss? How can I simulate this sort of things? So let's get there in a second. Yes, this one. So, but we want to prevent a situation like this, where, hey, I have circuit breakers. Everything is fine. Nothing's ever going to happen. But how do you know that you have selected the right timeout? How do you know that your circuit breakers are really catching everything? How do you know that your circuit breakers are returning default values for fail fast? So we have to test the circuit breakers, obviously. The easy way, and for which you don't need any tools, it's using the TC. That's a traffic control. That's actually part of Linux since kernel 2.4, so it's been there for a long time. With this tool, you can actually simulate latency in any package across any interface you like in your Linux servers, which is actually pretty interesting. So in this one, we're adding a delay of 1,000 milliseconds per package with a jitter of about 500 milliseconds. So basically, the actual delay will be anywhere between 500 and 1,500 milliseconds because the jitter is randomly added. So this actually gets us quite far already. So I can actually simulate latency for calls in my host, which is pretty good. But again, this only works in one host. So if you're actually running this on multiple hosts, you need to somehow orchestrate that this gets put in place before your test and so on. So it's actually nice, but pretty low level. We can do more things with actually TC, which is, I think it's a really cool tool. We can actually simulate TCP package corruption. We can simulate packet loss as well. So a couple of commands. This is installed out of the box. At least it was in my CentOS instance, so it's available there. But it's kind of low level. And our services work mostly with HTTP, so maybe we can use something a little nicer. We don't need to deal with command lines. We can do it in a more declarative way. So let's move on to HTTP fault injection. Now, this is exclusively for in the domain of HTTP. So when we're thinking of HTTP RESTful services, that's really where we can use these things. So what can these things do? So you have a service A. This thing sits like a proxy between yourself and service B. And what can it do? It can inject latency. They can inject bandwidth limits. They can inject timeouts. They can inject slow closing of the ports. They can inject data limits. So after a certain amount of kilobytes, close the connections. And they can do a bunch of other things. But these things are actually really what will simplify our testing for our resiliency and our circuit breakers. So there's one that I liked a lot, which is called ToxiProxy. And ToxiProxy, it's a proxy, and it adds what they call toxics, which basically are things like latency. And it works from the command line. It also has a Java API that I'll show you later. And what I'm going to do now is actually I'll show you ToxiProxy, and I'll show you the effect ToxiProxy can have on our circuit breakers so that we can actually verify whether they work at all or not. So we're going to do this. This is our previous setup. We're going to have an injection proxy in here, and then we'll have our to-do API client, so our Spring Boot thing, and then we'll see what happens. So let's do that. The first thing I need to do is I need to start my ToxiProxy client, which I have here, my ToxiProxy server. That's it. That's all it took for ToxiProxy to start. But it's empty, so I need to actually deploy my proxies. And what I did is I'm a big fan of Gradle, and this is not a Gradle session, but I use it a lot because it's very flexible. And I did add some Java code for setting up the different things I want to test with fallback, no, with ToxiProxy. Yes. So essentially, I could do this from the command line. So this is the equivalent command line tool for doing the command line call for doing that. But I like to do this through my build tool because then I can actually integrate this with my testing processes. So basically, I'm setting up a client and I'm creating a proxy, and I'm adding a latency proxy that adds 800 milliseconds plus 500 milliseconds of jitter, which means my calls will go between 300 milliseconds and 1.3 seconds in terms of latency. So that some go through, some don't. And then I can trigger my circuit breakers. And then I'm also adding a proxy for bandwidth in a different port that actually limits my throughput to 5 kilobytes a second. And that is still a thing. Every now and then you'll find edge, like 2G connections in mobile phones, and that's what you could test with these things. So I need to deploy this, so I'm going to use Gradle because, I'm a Gradle fan. Deploy proxies. That actually works. But if you prefer to use the command line, that's totally okay. So it's equivalent here. And this just deployed the proxies, which are now visible. And the main one, each proxy gets a different port. So you need to then modify your application so that you have a port. And then I will make this point to my port, so 8888. And that should be working. The thing I also added in here, which I'm going to, for a second, disable. I'm going to disable this because I want to show you the fail fast. Let's run this. Yeah, it works. Okay, there we are. So now we can go to our to-do, and some of these will not go through. It failed. This one failed because the latency was above a second, and my Histrix, my circuit breaker, stopped the call after a second. This one works, this one works, this one works. So you can see that the Toxic proxy is actually injecting some latency. So I'm actually live verifying my Toxic proxy. And you can see the circuit breaker is already showing things here. So let's do, let's go back to JMeter, and we can actually see the effect of that. Clear, and we run this. And now you'll see, now the circuit is closed because things seem to be getting through, but eventually circuit is open. Now things are not getting through because it triggered the circuit breaker, there's too much latency, so I'm returning errors actually. But I'm returning them very fast. You can see it's actually really fast. So that's the fail fast idea, right? The circuit breaker, so this is failing. I'm not going to let any more through because it's going to fail again. So just say it's an error and then try later in a little bit. And now it's still open, and eventually it should close again when it detects that things are flowing again. Well, actually it did already open because it was here. But again, you can see the dynamics here, right? My circuit breaker detects something is wrong. It keeps the circuit open. It keeps returning errors, and I'm getting a lot of errors, but it's going really fast. It's actually going faster than when I'm doing the right thing. And in this case, it's again closed. It actually noticed some things were getting through, so it's allowing calls. It's still kind of failing, but not so bad. And eventually, it will open it again because it failed. So now I'm actually empirically demonstrating that my circuit breaker is working, and it's preventing me from failures, and it's letting me return from an error situation without having to wait for that whole second, right? And if your timeout was 5 seconds for whatever reason, you wouldn't be making your clients wait for 5 seconds. You would be returning right away. Now, but that's still returning an error. So we talked about the graceful degradation, right? So how can we do that? And that's the part I just commented out. So what we can do is that in case of a fallback, we can define a fallback. So there's been an error, so there's two options. I can either tell my clients, hey, there's an error, deal with it, or I can tell them, well, you know, I did my best, it didn't work, this is what I could give to you in this situation, so try and work with it. In my case, the fallback is additional method. The fallback returns a to-do that says fallback, just for that so that we can see. But maybe you could return a list of empty to-dos and then let the client deal with that, right? The client tried to call, it got an empty list. Well, it's an error, it's better. So we can actually enable the fallback, and we can see now the difference when I activate the fallback and I start making the calls. And then I can make a call. I got an error before. Now, you see, I'm still getting it. This is a valid response. This is a valid to-do, but it's a fallback to-do, right? And in this case, it's clearly saying what it is. And then when some calls go through, I'll get the right one unless the circuit is now fully closed, which I don't know. Circuit is closed. I should eventually get a good one, but yes, now I got a good one, right? So I'm either getting the whole list when the latency is below a second because that's what my timeout is, or I'm getting a fallback response when it isn't. And then we can run again the test. Let me clear these so you can see the numbers. No errors. I'm still things are still getting through. The circuit is now closed. It will eventually open because it will keep failing. So there's a failure, and Histrix is catching it. The circuit breaker catches the failure, but it is not showing it to your client. So we have achieved quite easily the idea of that graceful degradation. It doesn't work. I'm failing fast, but I'm not really failing because I'm telling my clients, well, I'm returning this value to you. If you can work with it, fine, and then at least you don't get an error. And in many cases, this could be, you know, a value you cached, the last good known value you put in a cache, and then you return in case there's a failure. It could be anything that is relevant and semantically correct for the domain of your service. So I got no errors. This is great. My service now is technically resilient against the latency problems. So in a larger scale, we're not going to say it today, but you will integrate this with your CI testing processes, right? This is a Toxic proxy is just a server. You can run it anywhere. whenever you run your tests, deploy your proxies. Whenever your test is done, you can actually, I even build the support for, it's 2 lines of code for undeploying my test proxies. So you can do undeploy proxies. I don't know why it's not copying proxies. It undeploys my proxies, and then my toxic proxy server can be used for something else. So it's actually quite easy to integrate this with your CI testing processes. That was toxic proxy. Then toxic proxy it's a bit low level. There's an API which is kind of nice, but sometimes we prefer to use something a bit more declarative. There's another one which is called Toxi, and people who are creating this are not very original with the names. I don't know why, but there's another one called Proxy. It's written in Node.js, and it's not really it's not a server that you connect to and then you deploy proxies. It actually has an API, and then you actually write a bit of Node.js code, JavaScript code to set up the kind of things you want to do in there. In this case, the example I have is very similar. It has a latency. You can do, say, it's only for gets, and then a probability of 50 milliseconds. And I do have some code as well to show you how easy it is to run that sort of this one here. It actually is easy enough. And then when you want to run this thing, you simply go back to your console and Toxi, and then oh, that's good. Where did it go? Oh, good. Demo effect. That was far too long without a demo effect. Ah, it's latency, sorry. But this is the wrong folder. It's actually Toxi examples. And that's Toxi. And then all I need to do is go to my application, change the port for my calls, which is now 3000, and I can restart it. Not this one, but this one. Circuit breaker. Oops. W. And then my calls will go through the Toxi server. And the difference with this between this one and Toxi proxy, it's really whether you prefer to run command line or whether you prefer to create a bit more complex logic. The good thing about Toxi is that it lets you mix and match things. So that one is Toxi proxy is a bit more straightforward, either latency or bandwidth or one of the other toxics. This one you can actually mix them. You can have more complex logic and say only affect gets but not post inputs. And only affect specific number of requests. So in a way, this might be a little bit more flexible. And then same thing, some will go through, some will not go through. And it should be about 50%, which is actually being quite consistent. And then same thing, you can run your Hystrix monitor, run JMeter, and you should see approximately 50% failure. It's a little slower. Toxi is a little slower, but now it's that the circuit breaker is open. It's failing. It's not returning any error. It's returning the fallback value. But I'm again doing the same thing as before, just a different tool. So this is the tooling that we can use, that we have in place available. Yes, that was it about failure and resilience.
So, thanks, Oscar, for the very interesting demonstration and presentation. So, any comments or observations or any ideas?
I have one question, or a few maybe. Like basically, you can pretty much in a distributed systems you can manage your non-functional requirements basically with this, with tools like Hystrix and Toxi proxy. But is it at the same time like, are these tools like tools for the developers to see at the same time how their application code reflects to NFR? So does it like do the development cycle faster so that like maybe in a few years you don't actually need NFR testing that much? Is this making any sense?
Well, these are just tools. I mean, verifying that what I'm putting in here in my circuit breakers timeouts is according to your NFRs. It's still your responsibility. This will not do it for you. Because I set a second timeout because I know that's what it has to be. But you need to verify that that's correct. So these tools will not really do things for you. They'll help you in verifying that your data is correct and that it works as it should. But you still have work to do there. It's not silver bullet.
How about like designing Java architecture is pretty much design patterns and like OOP architecture. So are there like resilient like design patterns you have to take into consideration? Maybe I missed it, but
well, we had a few in the beginning, if you remember.
Okay.
So there are patterns that are specific. I mean, we can flip to the slides for a second. The ones I didn't cover today, those are actually useful. Specifically for very high needs for throughput and performance and resilience, you can look at the actor model. Yeah. But that's an entire thing by itself. We could spend hours talking about it. But you can look at that. You can look at back pressure models where the clients, the consumers, inform the producers, hey, you're going too fast. So there's a back channel for handling that back pressure. And say, you're going too fast, please slow down. You can use back pressure for dealing with these things. So, but in a way, what we saw today, it should address 95% of the resilience scenarios we're dealing with in normal cases. Of course, there'll be niche scenarios where you need to use actors and back pressure, but those are really, really specific sort of things.
In your last question is, in your experience, how easy it is to like apply these design patterns in applications?
Well, you need to see it. You usually see it coming, right? Someone tells you my service needs to respond as an NFR in like 50 milliseconds, and I'm going to be dealing with tens of thousands of requests a second. Maybe you want to look at something that is not the traditional request response model. Maybe you want to look at actors, and actors mean different framework, different programming model. It's really based on. It depends. It's very, very much consulting answer. It depends, but as an architect, you see that, right? That certain NFRs drive you to certain patterns, specifically in the resilience and performance space.
No more from me.
So do you have any questions? Yeah, sure.
How would you go about integrating the historic statistics and the state of the connection into your existing monitoring and alarming systems?
Good question. Hystrix exports the metrics. Actually, Hystrix through Spring Boot, in this case it's Spring Boot, but it specifically exports all its metrics data through StatsD. And I don't know if you know what StatsD is, but it's a very nice and lightweight protocol for exporting metrics data out of a service. And then through a metrics aggregator, you get that fed into your tool, and then from that you can do dashboards. So things like Sysdig, things like Grafana with Kibana, those will actually help you aggregate StatsD data. So you can actually get, because the dashboard is very much right here, right now. If you disconnect the dashboard, it doesn't keep historical data. So then you need to make sure you capture the StatsD metrics, push them to some metrics store, and then visualize them. And that can be done with StatsD support and in Spring Boot.
Thanks.
Okay, so do you have any questions? So actually I have one question in a way. So you mentioned that in a way there's a number of in a way known design patterns for fault tolerance and resilience, but you mentioned that still they are not in a way used as widely as they should be, for example, setting timeouts. So why do you think, what is the reason for this?
If I knew, I would have already fixed it everywhere. But sometimes, I mean, we approach things like interface or integration design and say, I need to call this other system. And it's easy enough that with 3 lines with HTTP client or REST template, you can make a call and then you forget about it. And it really is a matter of asking the right questions and knowing your requirements, something I was just now saying here, that you need to connect to some system. You will ask, how long should it take for response to come? How much load can this system take? And if the answers are strange or unusual, then maybe I should do something about it, like setting timeouts, like setting some sort of a circuit breaker to prevent me overloading that system, to prevent that system from screwing me up and kind of making me go slow. It's a matter of making the right questions at the right time, and we don't always do that, unfortunately.
Yeah. Okay, so thank you, Oskar.